So in this video, we're going to learn how to graph quadratic functions that contain both an a and a c value, but do not contain the middle b value. So to begin, I want to talk about what on earth a quadratic function is. So a quadratic function is going to use those quadratic equations that we've been working on solving. And a quadratic equation or a quadratic function, when it is graphed, will have a very specific shape that is called a parabola. So it's spelled and it looks like parabola, but it's really pronounced parabola. And parabola is this shape that you see in these three graphs here. So what you notice here is you have a very symmetrical U-looking shape. Sometimes it faces up, sometimes it faces down, and they can be positioned around different areas of the coordinate plane, but a quadratic will always have this parabola shape. So that's the shape we're going to expect to see in all of the graphs that we make. Then all of our equations, so that's what's going to go in this next blank, all equations with a highest variable exponent of exactly 2 will have this shape. So this is just talking about making sure we have equations that contain a highest variable exponent of 2. So things like y equals 3x squared plus 4x plus 5. So remember we talked about that quadratics are always polynomial equations that contain exactly a highest exponent of x of 2. So here we could also have y equals 25x squared minus 75. And we could also have something like y equals just x squared. Notice that the highest variable exponent for all of those is 2. Some non-examples would include y equals 3x plus 4. Notice how this x doesn't have a highest variable exponent of 2. This one actually produces a line. We could also have something like a non-example that looks like y equals 4x cubed plus 3x squared. Again, the highest variable exponent here is 3, so it doesn't meet the requirements of a quadratic. So now that we know what a quadratic function is, let's take a look at the parent graph of a quadratic function. So remember, these are second degree, so exponent of 2 functions or second degree polynomials. And our parent graph for our quadratic function is this simple graph here of just y equals x squared. So let's create a table of values for this equation so that we can see what the parent function of a quadratic function looks like. So here we're just going to take our values for x that we have here in our table. X is from 3 to negative 3, and we're going to plug them into our equation. So we have y is equal to 3 squared. Well, I know 3 squared is 9, so that would become 9. So I go to my graph, and I graph x is 3, y is 9. Then I go to my next one, y is equal to, x is now 2 squared. So that becomes 4. So I go to x is 2, y is 4. Then I go to the next one, y equals, this is 1 squared. So we have x is 1, y is 1. And then we have y is equal to 0 squared. That would be 0, so we're at 0, 0. Then we have y is equal to negative 1 squared, which is 1. Y is equal to a negative 2 squared, which is 4. And finally, y is equal to a negative 3 squared, which is 9. So here we can see that we have this parabola shape. We can see that it looks symmetrical, so if we connect all of those dots, and hopefully you'll be able to do a little better job than I am doing, we have that nice parabola shape for our graph. So this is the most basic, simplest quadratic function of just y equals x squared. Now our domain of this graph, we can see that it's going forever to the left and forever to the right. So our domain is simply all real numbers because we're using every single value for x and for y. And then our range here, we notice that we start, the lowest point is 0, and it goes up. We can see that here. It starts at 0, and then all of the y values go up. So our range is y is greater than or equal to 0. So all of the graphs that we make today will have this same general shape. It will have this U shape. And you'll see that it's just basically going to be a transformed version of this parent graph. It might be moved around, it might be stretched up and down, but it's going to be just a transformed version of this. Now, every single quadratic function is going to have two key components. And the first key component that you need to be able to find is called the vertex point. And the vertex point, by definition, is the point on the graph where the parabola changes direction. So here, if you look at this parabola and we kind of trace it along, we're starting on the left, it's going up, it's going up, it's going up, and then it reaches this important point up here at the top where it kind of then changes directions and starts going down. That's called our vertex point. And every single parabola will have a vertex point. The vertex point on this particular graph, where the graph changes direction, is the point x is 2, y is 1. And every single quadratic will have one of these points, and it's our job to identify it. So in addition to a vertex point, every single quadratic function will also have an axis of symmetry. And by definition, the axis of symmetry is a line drawn on the graph that divides the graph in half. So we can see here that if we were to draw a line that divided this graph in half, it would be about right here. Essentially, if I were to fold along that line, the parabola would in essence fold on itself perfectly. So this is called our axis of symmetry, and it is a line. So when we write down what our axis of symmetry is, we're going to write it down as the equation of a line. Now I notice here that I have a vertical line, and if I think back to earlier in the school year, my vertical line is represented by using x equals, in this case we have x is equal to 2. So every point on that line has an x value equal to 2, and y can be anything. So my axis of symmetry is a line of x is equal to 2. So let's just take a moment here and let's find the vertex and the axis of symmetry for each parabola below. So if I look at this first graph here, I notice that the graph starts off going down, and it changes direction right here at this point before it starts going up. So if I look at that particular point, that's going to be my vertex, and my vertex is the point x is 1, y is negative 4. And then if I look at the line that divides it in half, that line that divides it in half would be about right there. That's crossing through x equals 1 with all of the points on the line having an x value of 1. So my axis of symmetry is just 1. Then if I apply that same type of thinking to the next problem, here we have a point where it was going up, but now it's going down. So my vertex is that x is negative 3, y is negative 1. And then I look at my axis of symmetry. That's occurring when x is negative 3, always. So we're going to write that as x is equal to negative 3. So notice here that my vertex is always written as a point. My axis of symmetry is always written as a line. So we started to investigate what happens if we start to change our parent graph, which is right here in all black. So we have y equals x squared, we have all of our points, we found our domain and range, and we put that graph on our coordinate plane. And then what we did was we changed our a value to be 3. So we decided to see what happens if we change a to be 3. And what you're hopefully noticing here is that when we change a to be 3, what happens is we take all of these y points and we multiply them by 3. So they get 3 times bigger. And then as a result, when they get 3 times bigger, we can see on our graph that our graph gets a little bit skinnier. We can see that happening. The red graph is skinnier than the black graph. And we can see that all of our points essentially get stretched up. So the black point was here, that parent graph point was here, and it got stretched up to be 3 times taller. So we can also see that our graph gets stretched. So as we changed A to 3, we were able to see the graph get skinnier, and we were also able to see that graph get stretched up. So after we investigated A equals 3, we decided to investigate what would happen if A became 1/2. And what you should be seeing here again is that our parent graph is here in black. So you can see that we have our generic parent graph points, and we plotted them over on the graph in black. And then we applied the A value here in red. So what you should be seeing is that with an A value of 1/2, your Y value points actually got about half as tall, which kind of makes sense because we're basically taking our parent graph points and multiplying them by 1/2. Then if I look over here at this graph in red and compare it to the graph in black, I notice that this graph essentially got wider. And what it seems like happened was we took every parent graph value and we dropped it, or we shrunk it, to about half its height. So here this graph shrinks down to about half of its height. So when we change this A value to something very small like 1/2, the graph becomes wider and it shrinks down. And then lastly, we looked at what happens when we change A to be something that is negative, like a -1. So again, you can see our parent graph here in black, and you can see that as you multiplied these parent graph values by that -1A value, they all flipped and became a negative version of that. And then as a result, our graph vertically flipped over. So we can clearly see here that when we have an A value that is negative, it takes all of our parent graph values and it flips them over. And as a result of this, we also end up with a range that is slightly different, because that range is now taking place in the bottom half of the coordinate plane, which is when y is less than or equal to 0. So now let's take what we've learned and let's summarize it in our own words. So here it says what happens when the A value is greater than 1, or the absolute value of A is greater than 1. So this is saying something like A is equal to 3, or maybe -2, or 4, or -5, or something like that, where the distance from 0 of A is more than 1 unit away. And what we saw happen on our graph was our graph got skinnier, and our graph essentially got vertically stretched. We saw those points get stretched up from the parent graph. And these get vertically stretched, and essentially your graph becomes 3 times as tall, or 2 times as tall, 4 times as tall, 5 times as tall, etc. So when the absolute value of A, or the distance from 0 of A, was more than 1 unit away, that graph became vertically stretched. Then, when we looked at what happens when the absolute value of A is less than 1, so A is something like 1/2, or 1/3, or -3/4, or -0.8, something where the distance from 0 is less than 1 unit away from 0, our graph vertically shrank. So the example we saw was that x was 1/2, and it became essentially half as tall, or it might become 1/3 as tall, or 3/4 as tall, or 0.8 as tall. So we saw our vertical stretch and our vertical shrink that we've seen happen before. And then lastly, we noticed that when A happens to be a negative number, it could possibly have a vertical shrink or a vertical stretch, but if A is a negative number, it is also going to do what is called vertically flip. So for each equation below, we're just going to make a prediction about how the child graph that we see will differ from the parent graph. So in this first one, I see that I have an A value that is equal to 2/3. Because A's distance from 0 is less than 1 unit away, I know that this is going to be a vertical shrink by a factor of 2/3. So it's going to be 2/3 as tall as the parent graph. If I then look at the next example, here I see I have a -0.6 times x squared. So I can see that A is equal to a -0.6. So that negative automatically tells me that this is going to be a vertical flip. So it's going to flip over. And then that 0.6 has a distance from 0 that is less than 1 unit away. So this is going to be a vertical shrink by a factor of 0.6. So it'll be 0.6 times as tall. So now that we've got the a value down, let's try to incorporate some c values into our quadratic function. So here what we're going to do is we're just going to use the table to graph this particular equation. So we have y equals 2x squared minus 8, and all we're going to do is take this equation and we're going to substitute in values for x and calculate the corresponding y value. So here we can see we have y equals 2 times 3 squared minus 8. So I need to remember my order of operations here. I know that I do my exponent first, so that's going to become 2 times 9 minus 8. I then do my multiplication, so that's 18 minus 8, which my y value becomes 10. So I can graph that. I can say I have x is 3, y is 10. Then I move on to my next point where I have x is equal to 2. So I have y equals 2 times 2 squared minus 8. Again, I follow the order of operations. So I have 2 squared is 4. So 2 times 4 minus 8, which becomes 8 minus 8, which is 0. So my next point is x is 2, y is 0. Then my next point here, I take x is equal to 1. So I have y equals 2 times 1 squared minus 8. So I have 2 times 1 minus 8, which is 2 minus 8, which is negative 6. I then have x is 0, so 2 times 0 squared minus 8. Well, that's 2 times 0 minus 8, which is 0 minus 8, which is a negative 8. Then have y equals 2 times negative 1 squared minus 8. So 2 times 1 minus 8. So 2 minus 8 is a negative 6. So I can plot those 2 points there. I missed a couple. So 1, negative 6. 0, negative 8. And negative 1, negative 6. And then from here, y equals 2 times negative 2 squared minus 8. So I have 2 times 4 minus 8, which will be 8 minus 8, which is 0. So we end up with negative 2, 0 there. And then finally, my last one here, I have y equals 2 times negative 3 squared minus 8, which is 2 times 9 minus 8, which is 18 minus 8, which is simply 10. So we have x is negative 3, y is 10. So we can see here that we have that parabola shape that we expected. It's got that symmetry, and so now all we need to do is connect the points. So here's one half of our graph, and here is the other. There we go. Okay, so our domain of this graph, we can see it goes forever to the left and to the right. So we have all real numbers. In our range of this graph, we can see that the lowest point is when y is negative 8, and then it goes up. So we have all y values that are greater than or equal to negative 8. So while that took a little bit of time, we can see that actually graphing this using a table isn't too bad. We just have to use our order of operations and calculate all of the points.